Okay, so to follow up with what we were just doing, I want to say in general, if I have the integral of some function times y prime plus the derivative of that function times y, notice this derives to this. Actually, I should do it the other way. Whatever. That derives to that, and this derives to that. Okay, so that is the if I write that out, it's going to be equal to f of x times y. It's nothing more than just stating product rule. If I integrate, integrals and derivatives are opposite. The derivative of this is the innards of this, right? So that means that the integral of this side is going to be equal to that thing. So hopefully that makes sense, and I'm going to come back to this box a little bit later. So I'll give it a fancy, right? Okay, so let's keep going. So this is, like I said up top, this is 1.5 integrating factor. I'll sometimes just refer to it as mu. That is our integrating factor. And it is for solving what we call first order linear equations. And we talked about what first order and linear, or what order meant and linear versus nonlinear meant in the last class. So I'm just going to give you one example that is first order linear, and we will eventually solve this one. T, okay, so the other thing, I'm going to switch over to T's. Usually we have like Y and X as our independent variable, but I want you to start getting ready for T's, and pretty much everything else I'm going to do in this lesson will be T-based. So T is the independent variable. So T times Y prime minus Y is equal to T squared times e to the negative t. So this is linear. Why is it linear? Because all the t stuff doesn't affect whether it's linear or not, right? This right side over here, there's no y's or y primes, right? So this guy, this does not have to be linear. But look, I've got a y, right? That's linear because it's got a coefficient of 1. And then you may say, well, what about this y prime? Well, it doesn't matter if this is a function of t or not. In order for something to be linear, at least how we're going to categorize it, a linear differential equation is one for which the y's and the y primes, the dependent variable and its derivative, are not contained inside of another function. For example, they are not inside of a squared function or a sine function. Okay, so the first step that I do here is normalize. When I normalize it, I want the y prime term to not have anything on it. So that's going to have y prime. I'm going to divide by t basically. Minus 1 over ty equals, divide everything, so that means I got to divide the right side by t as well, t times e to the negative t. And that's the thing we're going to solve. If you were to try to fiddle with this, right? You know, could you use separation of variables? Could you use some other method that we know to integrate? You would just get stuck, right? So I need a trick to get my way out of it. One thing I'd like to point out is that it looks a little bit like this up here. Notice I've got a y and a 1 over t, right? And I've got a y prime here, right? So really I've got this y and the y prime, just like this, y and y prime. So I got a 1 over t. I don't have anything here. So the integrating factor is something that we multiply by. What I need to do is multiply this entire equation by something that I don't know yet that will make it so that it fits this thing right here. So I'll have a new, I will find something and I will multiply here and multiply here by that same thing and multiply over here by that same thing, such that I get something like this that is then integratable. If that didn't make sense, you could listen again, or you could just follow along for the ride and see what I'm talking about as we work through the math. And it's actually simple math. Now I'm going to step away from this particular equation right now, and I'm going to go into a more general form. So my generic first order linear, my generic form of these is going to be some function that I'll call f of t times y prime plus some other function, I'll call it g of t times y, is equal to a third function, h of t. Now notice that is this form, that's this guy. So in this case, f would be t, g would just be a -1, and then h would be t squared e to the negative t. So just like I did up here, I want to normalize it. So I'm going to divide by f of t. That gives me y prime equals, y prime plus g of t over f of t is, times y is equal to h of t over f of t. And this gets it into a form where hopefully, I will be able to, make it look like the rainbow box up here. All right, so, and I'll write that rainbow box down here a little bit lower when I'm ready for it. So now, I don't want all those F's, G's, H's, whatever, right? So I'm gonna rewrite it. I am going to let P equal G of t over f of t. So that is going to replace this. And then I am going to let Q equal h of t over f of t. So that will replace this. So what I wind up getting is y prime plus p of t times y is equal to some new function q of t. You may be like, well, why didn't you just give that in the beginning? Well, because a lot of times we aren't giving it to us. It isn't given to us in this way. It's given to us in the generic form, so I want to at least address that. Okay, so from here, what I need to do is I'm going to write this out. Well, I need to multiply by a function mu of t, that's my integrating factor, that we call an integrating factor. I don't know what mu is yet, but I need the mu to make the LHS, that's left-hand side of the equation, product rule backwards. So what we were doing up top. So let me show you what that looks like. I need mu, so I'm going to multiply everything in this equation right here by mu. So I'm going to get mu, and this is mu as a function of t, but I'm going to actually drop all the of t's, right? Just assume everything that I'm writing here, every letter is a function of t. So mu times y prime, both those are functions of t, plus mu times p times y is equal to q times, well, I should do it the other way around, but mu q. Sounds better that way anyway. All right, so look, let me pull up, I'll rewrite it, the little rainbow box from above, right? I'm going to pull up that guy. So, I know, and I'll just write it right here, that the integral of f of x y prime plus f prime of x y dx, and now we're working in t's, but whatever, is equal to f of x times y. Another way I could say this is that this derives to that. Now, look, these are exactly the same. This is this. This is this. This guy is all of that. Why is that? It's because the y here is there and the y here. So by process of elimination, they have to match up like that. So what I need, and I will write here, remember this derives to that, and this derives to that. So I'll pause for one moment to say that this is the first thing in this class where we have something that seems like totally not possible. I'm waving my hands, right? But totally not possible. And we just use some like little clever tricks to work our way out of the impossibility. We know product rule, and we get our good solid solution method. So all right, so let me keep going. So look here, this, let me do the dir arrows again. This needs to dir to that, because this already does dir to that. So let me write that. What that says is that the derivative, oops, let me go back to blue. The derivative, come on, man. The derivative with respect to time, actually I'm going to write it, make it more simple. Mu prime is equal to mu times p. That's what I need. If I have that, I get product rule. So how do I rewrite that? I get d mu dt is equal to mu times p. How do I solve this thing? Oh snap, it's separation of variables. So let's do that. D mu over mu is equal to p dt. Now I integrate. What's that give me? ln absolute value of mu is equal to the, I don't know what p is, so I'm just going to write, I'm going to leave it as the integral of p, and I'm going to write p of t dt, and then I can go and do my e to the, and that gives me my mu is equal to this right-hand side over here. So e to the integral of p of t dt. Now, that's it. That's mu. Okay? So if I have a function in this form up here, I just do e to the integral of this thing, and then that gives me the correct mu that's going to set it up so I can do product rule backwards, and it's all like it'll work perfectly. So in the next video, I will walk through what it looks like to solve for this e to the blah blah blah, right? What it looks like to solve for the mu in this equation right here.